The paradox of choice. Does freedom create anxiety? Imagine standing at a crossroads with countless paths stretching out before you. Each path represents a choice, a possibility, a different version of your future. The freedom to choose is exhilarating, but it can also be paralyzing. How do you know which path is the right one? And what if, after selecting, you look back and wonder, did I make the wrong decision? This is the paradox of choice, a concept that explores the tension between freedom and satisfaction. While we often think of choice as empowering, too many options can overwhelm us, leading to indecision, regret, and even anxiety. This paradox touches every aspect of modern life, from the mundane to the profound. It reveals how our search for happiness and fulfillment is often complicated by the freedom we deeply value. The psychology of choice. The paradox of choice was popularized by psychologist Barry Schwartz, whose research revealed that having more options doesn't always lead to greater happiness. The opposite is often true. The jam study. In a famous experiment, researchers set up a display of jams at a grocery store. On some days, the display featured 6 varieties, on others it featured 24. While more people were drawn to the larger display, they were less likely to buy a jam jar. This study demonstrated a key insight. Too many options can make decision-making more difficult, reducing our overall satisfaction with our choices. Decision paralysis. When faced with overwhelming choices, we often struggle to decide. This phenomenon, known as decision paralysis, occurs when our brains become overloaded with information, making it harder to weigh the pros and cons of each option. The fear of regret, even after we decide. The abundance of alternatives can lead to what Schwartz calls choice regret. We may second-guess our choice, imagining that one of the other options might have been better. Did you know this psychological effect isn't limited to major life decisions? It can happen in everyday situations, like choosing a meal at a restaurant or deciding what show to watch on a streaming platform. The more options we have, the harder it becomes to feel truly content with our choice. Modern life and the overload of choice, the paradox of choice, has become more relevant than ever in the modern world. We live in a time of unprecedented freedom, where technology and globalization have given us access to an almost infinite range of options. While this abundance offers incredible opportunities, it also comes with new challenges. Consumer choices, fallible, from clothing to electronics, that can be overwhelming. Studies show that consumers often feel less satisfied with their purchases when they have too many options. For example, when buying a pair of jeans, having dozens of styles, fits, and colors might seem appealing, but it can lead to frustration and doubt about whether the perfect choice was made. Lifestyle decisions. The paradox of choice extends beyond material goods to life's more significant questions. Where should I live? What career should I pursue? Should I settle down or keep exploring? People often feel pressure to make the perfect choice, with many available paths leading to stress and anxiety about missed opportunities. Social media and FOMO. In the digital age, social media amplifies the paradox of choice by constantly exposing us to the lives and choices of others. We see friends traveling to exotic locations, pursuing exciting careers, or enjoying seemingly perfect relationships, which can make our own decisions feel inadequate by comparison. This phenomenon, known as FOMO, further complicates our decision-making process as we increasingly worry about making the wrong choice. The philosophy of freedom and limitation. The paradox of choice raises profound philosophical questions about the nature of freedom and its relationship to happiness. While we often equate freedom with having unlimited options, the truth may be more nuanced. Freedom through simplicity. Philosophers like Soren Kierkegaard and Henry David Thoreau argued that true freedom comes not from having more choices, but from simplifying our lives. By focusing on what truly matters, we can reduce the anxiety and dissatisfaction from constantly seeking more. Did you know that the minimalist movement, which encourages people to live with less, is deeply rooted in this philosophy? Minimalists aim to create space for greater fulfillment and peace of mind by limiting their possessions and commitments. The value of constraints. In some cases, limitations can enhance creativity and satisfaction. For example, an artist with a limited palette may produce more focused and innovative work than one overwhelmed by infinite possibilities. Similarly, constraints in life can help us prioritize our values and make decisions more confidently. The illusion of the perfect choice, the paradox of choice, reminds us that no decision is ever truly perfect. Every choice involves trade-offs, and striving for perfection often leads to dissatisfaction. Instead, embracing good enough can help us find contentment in our decisions. Practical ways to navigate the paradox. While the paradox of choice highlights the challenges of modern decision-making, there are ways to navigate its complexities and find greater satisfaction in our choices. Simplify your options. Limiting the number of choices you consider can make decision-making more effortless and less stressful. For example, if you're shopping for a new laptop, focus on a few key features rather than comparing every model on the market. Set clear priorities. Knowing what matters most to you can help guide your decisions. By focusing on your core values and goals, you can filter out options that don't align with what truly matters. Embrace imperfection. Instead of striving for the perfect choice, aim for a decision that feels right in the moment. Remember that every choice comes with trade-offs, and it's okay to make mistakes. Practice gratitude. Gratitude is focused on what you gained rather than what you might have missed. Practicing gratitude can help shift your perspective and reduce regret or dissatisfaction. Reflections on choice and fulfillment. The paradox of choice reminds us that freedom is both a gift and a challenge. While the abundance of options in modern life offers incredible opportunities, it also requires us to navigate the complexities of decision-making with care and mindfulness. In the end, the value of a choice lies not in its perfection, but in how we embrace it. We can find greater peace and fulfillment by simplifying our lives, focusing on what truly matters, and letting go of the illusion of the perfect path. As you reflect on your choices, remember that the journey is as important as the destination. Each decision, no matter how small, shapes the story of your life. And in that story, every path holds its beauty and meaning. The Barber paradox. Self-reference and the limits of logic. Imagine a village with a single barber who prides himself on his precision and attention to detail. The barber follows a strict rule. He shaves all those in the town who do not shave themselves, and only those who do not. The rule seems simple and logical, but the question arises: who shaves the barber? If the barber shaves himself, he is breaking his own rule, as he only shaves those who do not shave themselves. But if he does not shave himself, then, by his rule, he must shave himself. This creates a contradiction, a logical impossibility at the heart of the Barber paradox. Understanding the Barber paradox. The Barber paradox, first introduced by mathematician and philosopher Bertrand Russell, is a thought experiment designed to illustrate the problems that arise from self-referencing. Its seemingly innocent question, who shaves the barber, reveals deeper issues with logic, language, and the foundations of mathematics. At its core, the Barber paradox demonstrates how self-referential statements can lead to contradictions. The barber's rule is self-referential because it applies to himself and others. This self-referential creates a loop that cannot be resolved logically. 1 minus 1, if the barber shaves himself, he does not follow his own rules. 2, if the barber does not shave himself, he must follow his rule and shave himself. This endless loop makes it impossible to determine the barber's actions without violating his rule, highlighting the limitations of logic when applied to certain types of problems. The connection to Russell's paradox. The Barber paradox is closely related to a more formal concept known as Russell's paradox, which Bertrand Russell discovered in 1901. Russell's paradox arises in set theory, a branch of mathematics that deals with collections of objects. To understand the connection, consider the following. A set is a collection of objects. For example, the set of all cats includes every cat in existence. Russell's paradox asks us to consider the set of all sets that do not contain themselves. If such a set exists, it creates a contradiction. If the set contains itself, then, by definition, it should not contain itself. If the set does not contain itself, it must contain itself to satisfy the definition of the set. This paradox revealed a fundamental problem with the foundations of set theory, prompting mathematicians to rethink how sets are defined and logical systems are constructed. The Barber paradox is a simplified version of Russell's paradox. It illustrates the same underlying issue using the idea of self-reconsistence. Both paradoxes demonstrate that self-recon systems can lead to contradictions, raising profound questions about the limits of logic and mathematics. Self-reference in philosophy and language, the Barber paradox and Russell's paradox are not just mathematical curiosities. They also touch on more profound philosophical questions about language, truth, and meaning. The liar paradox. Consider the statement, "This statement is false." If the statement is true, it must be false, as it claims. But if it is false, then it must be true. This creates a logical loop similar to the Barber paradox, where self-recreation leads to contradiction. The liar paradox has fascinated philosophers for centuries. It highlights the challenges of defining truth and the limitations of language. Gödel's incompleteness theorems. In the 20th century, mathematician Kurt Gödel built on these ideas with his incompleteness theorems, demonstrating that any sufficiently complex mathematical system contains statements that cannot be proven or disproven within the system. Gödel's work revealed the inherent limitations of logical systems, showing that self-section is not just a philosophical curiosity, but a fundamental aspect of reality. Language and meaning, the Barber paradox, also questions how we use language to describe the world. When a rule or statement applies to itself, it can create ambiguity and confusion, challenging our ability to define meaning clearly. Language's self-referential nature reminds us that human understanding is not always as precise or objective as we might think. Self-reference in modern science and technology. The Barber paradox poses challenges that extend beyond philosophy and mathematics. Self-recognition is crucial in computer science, artificial intelligence, and systems theory. Recursive algorithms. Many computer programs rely on recursive algorithms, processes that refer back to themselves to solve problems. While these algorithms are powerful, they can also create infinite loops if not carefully designed, echoing the logic of the Barber paradox. Artificial intelligence and self-improvement. Some AI systems are designed to improve themselves by analyzing their code. This self-referential process raises questions about AI's limits and whether self-improvement can lead to unintended consequences, such as paradoxical behavior or ethical dilemmas. Feedback loops in systems. Self-referential feedback loops also appear in systems theory, where they can lead to instability or unexpected outcomes. For example, in economics, self-referential behavior can create market bubbles, where the perception of value drives itself upward until the system collapses. Reflections on the Barber paradox. The Barber paradox may never have a clear solution, but its beauty lies in the questions it raises. It reminds us that logic, for all its power, has limits. Not every question can be answered, and not every rule can be applied universally. This paradox also invites us to reflect on the nature of self-refutism and the challenges it creates. Whether in mathematics, philosophy, or everyday life, self-recognition forces us to confront the complexity of reality and the boundaries of our understanding. Ultimately, the Barber paradox is not just about a barber or a village. It is a metaphor for the human condition. It reminds us that life is full of contradictions and that some mysteries are meant not to be solved but to be appreciated. Today, I'm proud to be part of something that is rooted in egotism. Schrödinger's cat, the nature of reality. In the world of quantum mechanics, where particles behave in ways that defy common sense, one paradox stands out as a symbol of the strange and counterintuitive nature of reality. Schrödinger's cat. This thought experiment, proposed by physicist Erwin Schrödinger in 1935, was designed to illustrate the peculiar consequences of quantum theory. It asks us to imagine a cat placed inside a sealed box, along with a radioactive atom, a Geiger counter, and a vial of poison. The setup is simple. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If the atom does not decay, the cat remains alive. However, according to quantum mechanics, the atom exists in a superposition of states, both decayed and not decayed, until it is observed. This means the cat is simultaneously alive and dead, existing in two states, until someone opens the box. The mystery of superposition. The concept of superposition is at the heart of quantum mechanics. It suggests that particles like electrons can exist simultaneously in multiple states or positions until they are measured or observed. This idea is deeply counterintuitive. After all, in our everyday experience, things exist in definite states. A coin is either heads or tails, not both simultaneously. Instead of having definite properties, particles exist as probabilities, described by a wave function. The wave function represents all the possible states a particle can occupy, and it collapses into a single state when observed. In Schrödinger's cat, the superposition of the atom's decay state creates a superposition for the cat itself. Until the box is opened, the cat is alive and dead, existing in a strange liminal state that defies our usual understanding of reality. The role of the observer. One of the most profound implications of Schrödinger's cat is the role of the observer in shaping reality. In quantum mechanics, the act of measurement, or observation, appears to determine the outcome of a system. Before the observation, the system exists in a superposition of states, but once it is observed, it collapses into a single, definite state. This raises profound questions about the nature of reality. Does observation create reality? If observing collapses the wave function, does that mean reality depends on our perception? Is the universe fundamentally indeterminate until it is observed? What counts as an observer? Does observation require a conscious mind, or can it be performed by inanimate objects such as measuring devices? This question touches on the physical and philosophical boundary, challenging our understanding of what it means to observe something. Does reality exist independently of observation? Schrödinger's cat forces us to confront the possibility that the universe operates in ways that are fundamentally different from our everyday experiences, where reality seems independent of our actions. The Copenhagen interpretation and beyond. Schrödinger's cat was initially intended to critique the Copenhagen interpretation of quantum mechanics, which states that the wave function collapses into a definite state upon observation. While this interpretation remains one of the most widely accepted frameworks in quantum physics, it has challenges and alternatives. The many worlds interpretation. According to the many worlds interpretation, the wave function never collapses. Instead, every possible outcome of a quantum event occurs in a separate, parallel universe. In the case of Schrödinger's cat, one universe contains a living cat, while another includes a dead cat. These universes coexist, branching off one another at the moment of measurement. This interpretation removes the need for wave function collapse, but introduces the mind-bending idea of infinite parallel realities, decoherence, and quantum realism. Another explanation involves quantum decoherence, a process in which the superposition of states interacts with the environment, causing it to appear as though the wave function has collapsed. Decoherence suggests that the cat's superposition becomes entangled with its surroundings, making the system behave in a way that resembles classical reality. Objective collapse theories. Some physicists propose that the wave function collapses independently of observation. These objective collapse theories aim to reconcile quantum mechanics' probabilistic nature with classical physics' deterministic nature. Schrödinger's cat in philosophy and culture. Beyond its scientific implications, Schrödinger's cat has become a powerful metaphor for ambiguity, duality, and the limits of human understanding. It has inspired countless philosophical debates and cultural works that explore the tension between potentiality and reality. Philosophical implications. Schrödinger's cat challenges our assumptions about what it means for something to exist. Is existence binary, alive or dead, true or false, or is it a spectrum of possibilities? The paradox also invites us to consider the relationship between perception and reality. If our observations shape the universe, to what extent do we create the world around us? Cultural impact. The thought experiment has entered popular culture as a symbol of uncertainty and paradox. From films like Donnie Darko to TV shows like The Big Bang Theory, Schrödinger's cat has become shorthand for the mysteries of the quantum world. Did you know that Schrödinger's cat is often used in art and literature as a metaphor for the human experience, representing the complexity of choice, identity, and potential? Reflections on the nature of reality. Schrödinger's cat is more than a thought experiment. It is a window into the fundamental nature of reality. It reminds us that the universe operates on scales that defy intuition, where particles can exist in multiple states, and observation plays a central role in shaping what we perceive. But Schrödinger's cat's beauty lies not in its resolution, because it has none, but in the questions it raises. It invites us to embrace uncertainty, marvel at the quantum world's complexity, and reflect on our place. As we move forward on this journey through paradoxes, let us carry with us the lessons of Schrödinger's cat, that reality is not always as it seems, that observation and perception are intertwined, and that the mysteries of the universe are as profound as they are beautiful. The Fermi paradox. Where is everyone? When we gaze up at the night sky, we are reminded of the vastness of the universe, a seemingly infinite expanse filled with billions of galaxies, trillions of stars, and even more planets. With such a staggering number of worlds, the idea that we might be alone seems improbable, even absurd. And yet, as far as we know, humanity remains the only intelligent civilization. This contradiction between the high probability of extraterrestrial life and the lack of evidence for it is known as the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox challenges us to reconcile the cosmos' vastness with the stars' silence, the scale of the universe, and the probability of life. The Fermi paradox begins with a simple observation. The universe is unimaginably vast, and the conditions for life appear to be relatively common. Astronomers estimate that there are over 200 billion stars in our galaxy alone, with each star hosting, on average, one or more planets. Many of these planets lie in the habitable zone, the region around a star where conditions are just right for liquid water to exist, a key ingredient for life as we know it. The numbers become almost incomprehensible when we expand our view to include the billions of galaxies beyond the Milky Way. With so many life opportunities, the probability of intelligent civilizations existing elsewhere seems overwhelmingly high. The Drake equation. Developed by Frank Drake in 1961, the Drake equation estimates the number of active communicative extraterrestrial civilizations in our galaxy. It considers factors such as the rate of star formation, the fraction of stars with planets, the likelihood of life arising, and the lifespan of technological civilizations. Even with conservative estimates for each variable, the equation suggests that there should be thousands, if not millions, of advanced civilizations in the Milky Way alone. The commonness of life, recent discoveries of exoplanets have reinforced the idea that abundant planets capable of supporting life exist. Some of these worlds, such as those in the TRAPPIST-1 system, even have multiple Earth-sized planets within their habitable zones. Additionally, the building blocks of life, amino acids, water, and organic molecules, have been found throughout the galaxy, from the icy moons of Jupiter to interstellar clouds. Considering all these factors, the question remains: if intelligent life is so likely, why haven't we found it? Potential solutions to the Fermi paradox. Scientists and philosophers have proposed numerous solutions to the Fermi paradox, each offering a unique perspective on why we haven't encountered extraterrestrial civilizations. We are alone. One of the most straightforward explanations is that intelligent life is rare or unique to Earth. While microbial life might be ordinary, The evolution of complex, intelligent organisms could require a series of highly improbable events. Did you know that the emergence of human intelligence on Earth depended on numerous chance occurrences? From the asteroid that wiped out the dinosaurs to the specific climate conditions that allowed early humans to thrive. The Great Filter. Another possibility is the existence of a great filter, a barrier that prevents life from advancing to the stage of interstellar communication. This filter could occur at any point in a civilization's development, from the origin of life to the mastery of advanced technology. If the Great Filter is in our future, it suggests that most civilizations will destroy themselves before they can explore the stars. Nuclear war, climate change, and resource depletion are often cited as potential filters. They are too far away. The vast distances between stars and galaxies might make communication or travel impossible. Even the closest stars are light years away, meaning signals or spacecraft would take decades or millennia to reach us. Additionally, the sheer scale of the universe means that civilizations could exist but remain forever out of our reach due to the limitations of physics and technology. They are hiding or ignoring us. Some theorists suggest that extraterrestrial civilizations might deliberately avoid contact with us. This could be due to ethical considerations, example, preventing interference with less advanced species, or practical concerns, example, conserving resources. This idea is sometimes called the zoo hypothesis, which likens humanity to animals in a cosmic zoo being observed from a distance. We are not listening in the right way. It's also possible that we simply haven't developed the right tools or methods to detect extraterrestrial signals. Advanced civilizations might use forms of communication beyond our current understanding, such as neutrinos or gravitational waves. The search for extraterrestrial intelligence, SETI. The search for extraterrestrial intelligence, SETI, represents humanity's effort to answer the Fermi paradox. For decades, scientists have used radio telescopes and other tools to scan the skies for signs of intelligent life. Listening to the Cosmos SETI programs focus on detecting radio signals that might originate from advanced civilizations. These signals stand out from the universe's background noise, indicating deliberate communication. In 1977, a strong and unusual signal, known as the WOW signal, was detected by a radio telescope. While its origin remains a mystery, it has become a symbol of the potential for discovery. Exploring exoplanets. Technological advances have allowed scientists to study the atmospheres of exoplanets for signs of life. For example, oxygen, methane, or other biosignatures could indicate biological activity. Future missions, such as the James Webb Space Telescope, aim to explore exoplanets in greater detail, bringing us closer to answering whether we are alone. Challenges and limitations. Despite decades of effort, no definitive evidence of extraterrestrial intelligence has been found. This raises questions about the effectiveness of our methods and the likelihood of success. Philosophical reflections on the Fermi paradox. The Fermi paradox is not just a scientific question, but a deeply philosophical one. It forces us to confront our place in the universe and the meaning of our existence. The loneliness of the cosmos. If humanity is truly alone, what does that say about our significance? Does it make us unique, or does it emphasize the fragility of life in an indifferent universe? The beauty of the unknown. Alternatively, the silence of the cosmos could remind us of the vastness of the unknown. It invites us to imagine the possibilities that lie beyond our understanding and embrace the mystery of the stars. A call to responsibility. If we are the only intelligent civilization, it places a profound responsibility on humanity to preserve and protect life on Earth. Our actions could shape the universe's fate in ways we cannot yet comprehend. Reflections on the search for others. The Fermi paradox reminds us that the universe is humbling and inspiring. Whether alone or part of a vast, unseen community of civilizations, the cosmos's silence challenges us to think deeply about our place. As we search for answers, remember that the journey is as important as the destination. Each question we ask, each star we study brings us closer to understanding the universe and ourselves. The twin paradox: time travel in reality. Time travel has long fascinated human imagination, inspiring countless works of science fiction. However, within physics, the concept of time travel isn't merely a fantasy, it is a consequence of the laws of nature, particularly Einstein's theory of relativity. The twin paradox, one of physics's most famous thought experiments, explores how time can behave in ways that defy intuition, bending and stretching depending on one's frame of reference. Imagine two twins. One remains on Earth, while the other embarks on a journey into space aboard a spacecraft traveling at nearly the speed of light. When the traveling twin returns to Earth, they find their sibling has aged significantly more than they have. This is the twin paradox, which reveals the strange and counterintuitive nature of time dilation. The basics of time dilation. At the heart of the twin paradox is time dilation, a consequence of Einstein's theory of special relativity. Time dilation occurs because time does not flow at a universal, fixed rate. Instead, it is relative. It depends on the motion of an observer relative to another observer. Relativity and the speed of light. According to special relativity, the speed of light is the same for all observers, regardless of their motion. This principle has profound implications for time and space, requiring them to adjust to maintain the constancy of light. As an object approaches the speed of light, time slows down for that object relative to an observer at rest. This is not an illusion, but a fundamental feature of the universe. The twin paradox explained. Due to their high velocity, the twins aboard the spacecraft experience time moving more slowly. Meanwhile, the twins on Earth experience time at their usual rate. When the traveling twin returns, they will age less than their sibling because less time has passed for them during their journey. This effect has been experimentally confirmed. For example, exact atomic clocks placed on fast-moving aircraft have been shown to tick more slowly than identical clocks on the ground, consistent with the predictions of relativity. Why is it a paradox? At first glance, the twin paradox violates the principle of relativity, which states that the laws of physics are the same for all observers. After all, from the perspective of the traveling twin, it is the earthbound twin who appears to be moving, so why wouldn't time slow down for them instead? The resolution lies in the traveling twin, which involves acceleration and deceleration, breaking the symmetry of the situation. Unlike the twin on Earth, who remains in an inertial, non-accelerating frame of reference, the traveling twin experiences changes in velocity as it turns around to return home. These accelerations and decelerations make the situations of the two twins fundamentally different, resolving the apparent paradox. The physics of space-time. The twin paradox is not just a thought experiment. It reveals the fundamental nature of the universe as described by relativity. Time and space are not separate entities. They are part of a unified structure called space-time, shaped by motion and gravity. The nature of space-time, in Einstein's framework, time is not absolute but relative, depending on the observer's velocity and gravitational environment. The traveling twins' high velocity through space causes their path through space-time to differ from that of the earthbound twin, resulting in the observed difference in aging. Gravity and general relativity, the effects of time dilation are not limited to motion. In general relativity, gravity also warps space-time, causing time to pass more slowly in stronger gravitational fields. For example, clocks on the Earth's surface tick more slowly than those on satellites in orbit, a difference that must be accounted for in technologies like GPS. Philosophical implications of the twin paradox. The twin paradox is not just a scientific phenomenon, it also raises profound philosophical questions about the nature of time, reality, and human experience. What is time? Time feels intuitive. We experience it as a steady flow, moving from past to future. But the twin paradox challenges this notion, revealing that time is malleable and subjective. Is time a fundamental aspect of reality, or is it a construct of our perception? If time can stretch and bend, What does that say about the nature of the universe? Relativity and the human experience. The twin paradox highlights the relativity of human while therein. The traveling twins' journey may fief while decades pass for their sibling on Earth. This disparity forces us to consider the role of perspective in shaping our understanding of reality. Immortality through time dilation. The paradox also raises intriguing possibilities for space travel. If a spacecraft could approach the speed of light, its passengers would experience time at a fraction of the rate observed on Earth. Could this be a form of immortality, allowing humans to travel far into the future while aging minimally? Time travel, science or science fiction. While the twin paradox demonstrates that time travel to the future is possible in principle, traveling to the past remains a far more significant challenge. Theoretical solutions, such as wormholes and closed time-like curves, have been proposed, but they remain speculative and fraught with their paradoxes. Wormholes as time machines, wormholes hypothetical shortcuts through space-time, could allow for travel between different points in time. However, their stability and existence remain unproven. Even if wormholes could be created, they would likely require exotic forms of matter to keep them open, posing significant technical and theoretical challenges. The role of quantum mechanics. Some physicists suggest that quantum mechanics could provide insights into the nature of time and its potential for manipulation. For example, quantum entanglement, where particles remain connected across vast distances, hints at the possibility of information transfer that defies classical concepts of time. Reflections on time and the twin paradox. The twin paradox reminds us that time is not as fixed or straightforward as it seems. It is a dynamic, flexible dimension that shapes and is shaped by the universe. Exploring it can help us gain a deeper understanding of the cosmos and a renewed sense of wonder at the mysteries of existence. As we continue our journey through paradoxes, let us carry with us the lessons of the twin paradox. That time is both a scientific reality and a profound mystery, and that our quest to understand it will always be as much about philosophy as it is about physics. The paradox of the infinite. Can the universe truly be boundless? For centuries, the concept of infinity has fascinated and perplexed humanity. It represents something without limits, something boundless and immeasurable. But while infinity is a cornerstone of mathematics and cosmology, it is also profoundly paradoxical, raising questions about the nature of existence and the universe. Is the universe infinite? Does space stretch on forever? Or does it have an edge, a boundary beyond which nothing exists? If the universe is infinite, what does that mean for its contents? Are there infinite stars, galaxies, or even infinite versions of ourselves? These questions lie at the heart of the paradox of the infinite, a profound mystery that challenges our imagination and understanding of reality. The mathematics of infinity. Infinity is a well-defined concept in mathematics, yet it defies our intuitive understanding of numbers and quantities. It is not a number in the usual sense, but an idea, a way of describing something without end. Countable versus uncountable infinity. Mathematicians distinguish between different types of infinity. For example, the set of natural numbers, 1, 2, 3, is countably infinite because its elements can be listed in sequence. In contrast, the set of real numbers, which includes all fractions and decimals, is uncountably infinite, meaning its elements cannot be listed in a sequence. This reveals that some infinities are more extensive than others, which seems almost contradictory. Hilbert's Hotel. A famous thought experiment called Hilbert's Hotel illustrates the paradoxical nature of infinity. Imagine a hotel with an infinite number of rooms, all of which are occupied. If a new guest arrives, the hotel can still accommodate them by shifting every existing guest to the next room, freeing up room 1. This paradoxical scenario demonstrates that infinity behaves in ways that defy our usual expectations, challenging our understanding of space, time, and logic. Infinity in cosmology, the nature of the universe. When we apply infinity to the universe, it takes on even greater significance. Cosmology, the study of the universe's origin, structure, and fate, grapples with questions at the intersection of science and philosophy. Is the universe infinite? Observations suggest that the universe is flat on a large scale, meaning it does not curve back on itself like the surface of a sphere. This flatness implies that the universe could be infinite, extending forever in all directions. However, even if the universe is finite, it may have no boundary, much like the surface of a sphere, which is finite but unbounded. This raises the question, how can something have no edge but still be limited in size? Infinite galaxies and stars. If the universe is infinite, it contains infinite galaxies, stars, and planets. This has staggering implications, including the possibility of endless copies of our solar system, or even infinite versions of you scattered across the cosmos, the observable universe. While the universe may be infinite, we can only observe a finite portion of it, limited by the speed of light and the age of the cosmos. Beyond the observable universe lies a realm we can never see or interact with, raising questions about whether infinity truly exists or is simply a theoretical construct. The paradox of the infinite in philosophy. Philosophers have long grappled with the paradoxical nature of infinity, exploring its implications for existence, knowledge, and the universe. Zeno's paradoxes revisited. Zeno of Elea, the ancient Greek philosopher, introduced several paradoxes that touch, such as the dichotomy paradox and the arrow paradox, on infinity. Such as thought experiments challenge our understanding of motion, time, and space, revealing and realities of reconciling infinity with everyday experience. The infinite regress problem. The concept of infinity also appears in philosophical debates about causality and existence. For example, if there is a cause, and every issue has a prior cause, this leads to an infinite regress. Does this chain of causation stretch back forever, or is there a first cause outside the chain? The mystery of eternal time. If time is infinite, does it have a beginning or an end? Does it have a beginning or an end? Some philosophers argue that the concept of eternity, a state of timelessness, offers an alternative to the paradoxes of infinite time. Still, this idea raises questions about the nature of existence. Infinity in modern physics. In modern physics, infinity emerges in some of the most profound and challenging theories about the universe. Singularities in black holes. At the center of a black hole lies a singularity, where gravity becomes infinite and the known laws of physics break down. Singularities represent a paradox in our understanding of the universe and highlight the limits of our current theories. The multiverse hypothesis. Some cosmological theories propose that our universe is just one of many in a vast multiverse, which could be infinite. Each universe might have different physical laws and constants, creating endless possibilities. Quantum mechanics and infinity. In quantum mechanics, infinity appears in calculations involving virtual particles, probabilities, and the behavior of fields. While mathematical techniques like renormalization help manage these infinities, their presence raises fundamental questions about the nature of reality. Reflections on the infinite. The paradox of the infinite challenges us to confront the limits of human understanding. It reveals the tension between our existence's finite nature and the cosmos's boundless possibilities. Infinity is not just a mathematical or scientific concept. It is philosophical and existential. It invites us to imagine the unimaginable, embrace the mystery of the unknown, and reflect on our place in a universe that may have no end. As we continue to explore the paradoxes of existence, let us remember that infinity is both a puzzle and a source of inspiration. It reminds us that the universe is vast, complex, and profoundly mysterious, and that our journey of discovery is far from over. The Bootstrap paradox. Can the past create itself? Imagine you find an old book filled with knowledge far beyond its time. The book's author is unknown, and as you study its contents, you use the information to make groundbreaking discoveries. Years later, you recreate the book and leave it for your younger self to find. But this raises a perplexing question. Who wrote the book in the first place? If the knowledge existed only because you brought it back from the future, where did it originate? This is the Bootstrap paradox, a mind-bending scenario that questions the nature of causality and the flow of time. The word bootstrap comes from pulling yourself up by your bootstraps, a metaphor for achieving something impossible. In this paradox, an object, piece of information, or event exists without a clear point of origin, seemingly creating itself in an endless loop. Understanding the Bootstrap paradox. At its core, the Bootstrap paradox involves a loop of causality in which an object or piece of information exists without an identifiable origin. It defies our intuitive understanding of cause and effect, where every event has a preceding cause. Consider these examples. The time traveler's gift. A person travels back in time and gives a younger version of themselves a unique artifact, a watch, for example. The younger version keeps the watch and later becomes the older version, who travels back in time to give it to their younger self. The watch exists, but it has no point of creation. It simply exists within the loop. The composer's symphony. A composer from the future travels back in time and transcribes a symphony written by a famous composer. The younger composer publishes the symphony, which becomes famous and inspires the older version to bring it back in time. Who, then, is the actual author of the symphony? The Bootstrap paradox challenges the idea that time flows in a linear cause and effect sequence. Instead, it suggests that events can form closed loops, where the future influences the past just as much as the past shapes the future. The role of causality in time travel. The Bootstrap paradox arises in the context of time travel, where the standard rules of causality break down. In our everyday experience, causes precede effects. Dropping a ball causes it to fall, and striking a match causes it to ignite. However, time travel introduces the possibility that the impact influences the causes, creating a loop that defies explanation. Causal loop. In a causal loop, an event is the cause and the effect of itself. For example, a time traveler may go back and inspire an event that ultimately leads to their journey into the past. While causal loops are consistent within themselves, they raise questions about the origin of the events within the loop. Where did the chain of causality begin? Temporal consistency. Some physicists argue that causal loops must be self-consistent and not create contradictions. For example, a time traveler cannot change events in a way that would prevent their journey into the past. This principle, known as the Novikov self-consistency principle, ensures that time travel does not violate the logical structure of the universe. The nature of time. The Bootstrap paradox forces us to reconsider the nature of time. Is it a linear progression from past to future? Or is it more like a tapestry, where events are interconnected in complex and non-linear ways? Philosophical implications of the Bootstrap paradox. The Bootstrap paradox raises philosophical questions about existence, causality, and free will. The problem of origin. The paradox highlights the origin problem. Where did it come from if an object or piece of information exists within a causal loop? Is it independent, or is it a product of the loop itself? This challenges our traditional understanding of creation and existence, suggesting that some things may exist without a clear cause. Free will and determinism. In a causal loop, events are predetermined by their structure. If the future influences the past, does that mean free will is an illusion? Or does the paradox suggest that free will operates within the constraints of time's interconnected web? The nature of reality. The Bootstrap paradox invites us to question the nature of reality itself. If time is not linear, our perception of cause and effect may be a simplified version of a far more complex truth. Examples in science fiction and culture. The Bootstrap paradox has become a staple of science fiction, serving as a narrative device to explore the mysteries of time travel and causality. movies and TV shows. In the movie Predestination, the entire plot revolves around a complex web of causal loops where characters unknowingly create their pasts and futures. In Doctor Who, the Bootstrap paradox is explored through episodes like Blink and The Big Bang, where time travel creates self-contained loops of events. Literature, books like The Time Traveler's Wife and All You Zombies use the Bootstrap paradox to explore themes of love, identity, and destiny. Did you know that H.G. Wells's The Time Machine hints at similar ideas, with the traveler's actions influencing the future in unforeseen ways? Cultural metaphors. The paradox has also entered popular culture as a metaphor for circular reasoning, where conclusions rely on their premises. Reflections on time and causality. The Bootstrap paradox challenges us to rethink everything we know about time, causality, and existence. It reveals the fluidity of cause and effect, the interconnectedness of past and future, and the profound mysteries at reality's heart. As we reflect on the paradox, we are reminded that the universe is not bound by our intuitive understanding of time. Instead, it operates on scales and principles that defy explanation, inviting us to embrace the beauty of the unknown. The Olbers paradox. Why is the night sky dark? Looking up at the night sky, we see a universe full of stars. Yet, for all its brilliance, the sky is predominantly dark. This darkness may seem ordinary, but it raises a profound question. If the universe is infinite and filled with stars, why isn't the night sky as bright as the sun? This is the essence of Olbers' paradox, a mystery first articulated in the 19th century by German astronomer Heinrich Wilhelm Olbers. On the surface, the paradox seems simple, but its implications touch on the nature of the universe, the limits of human perception, and the mysteries of space and time. The paradox explained: a universe full of stars. Olbers' paradox begins with a seemingly logical assumption. If the universe is infinite, eternal, and uniformly filled with stars, then every line of sight should eventually land on the surface of a star. This would mean that the entire sky should glow as brightly as the surface of the sun. Yet when we look at the night sky, we see vast stretches of darkness punctuated by pinpoints of light. This contradiction raises the question, what prevents the night sky from being uniformly bright? To understand the paradox, consider these points. Infinite stars, infinite light. In an infinite universe, the number of stars should also be endless. Their light would overlap, creating a continuous glow across the sky. The farther a star is, the fainter its light appears due to distance. But in an infinite universe, the sheer number of distant stars would compensate for their faintness, resulting in a bright sky. The reality of darkness. Despite these assumptions, the night sky remains mostly dark. This discrepancy suggests that something about our understanding of the universe, or the nature of light itself, is incomplete. Scientific solutions to the paradox. Over the centuries, scientists have proposed various solutions to Olbers' paradox, each revealing more profound insights into the nature of the cosmos. The finite age of the universe. One key solution is that the universe is not eternal. It has a finite age of approximately 13.8 billion years. This means we can only see light from stars whose light has had time to reach us since the Big Bang. Did you know that light from the most distant galaxies takes billions of years to reach us? Beyond a certain distance, the light from stars has not yet had enough time to reach Earth, leaving those regions of the sky dark. The expanding universe. The universe is not static. It is expanding, as discovered by Edwin Hubble in the 20th century. This expansion stretches the wavelengths of light from distant stars, shifting it into the infrared and microwave portions of the spectrum, where it becomes invisible to the naked eye. This red-shifted light contributes to the faint glow of the cosmic microwave background, CMB, the absorption of light. Interstellar dust and gas absorb some of the light stars emit, preventing it from reaching Earth. While this absorption is not the primary reason for the night sky's darkness, it shapes the universe's overall brightness. The role of the Big Bang. The Big Bang provides a critical framework for understanding Olbers' paradox. In a universe that began as a singularity, time and space have a clear origin, and the observable universe is finite in size, the cosmic horizon. The speed of light and the age of the cosmos limit the observable universe. This creates a cosmic horizon beyond which we cannot see, as light from those regions has not yet reached us. Beyond this horizon, the universe may be filled with stars, but their light is effectively hidden from view, contributing to the night sky's darkness, the early universe. Moments after the Big Bang, the universe was filled with dense, hot plasma that emitted light. As the universe expanded and cooled, this light shifted into the microwave portion of the spectrum, becoming the cosmic microwave background. The faint glow of the CMB reminds us of the universe's origins. It also offers a solution to Olbers' paradox by explaining why we do not see infinite starlight. Philosophical reflections on darkness and light. Olbers' paradox is more than a scientific question. It is a philosophical one that invites us to reflect on the nature of existence and perception. The beauty of contrast. The dark night sky's darkness to appreciate the light of the stars. Without three darkness, then darkness would be lost. Din without darkness. Presence and absence define each other. Where light and darkness, presence and absence, define each other, the limits of perception. Olbers' paradox reminds us that our perception is limited. The darkness we see is not an absence of light, but a boundary imposed by the nature of the universe itself. This limitation invites humility, reminding us that much about the cosmos remains beyond our reach. The mystery of the infinite. The paradox also touches on the concept of infinity. If the universe is infinite, then the night sky's darkness reveals the interplay between the infinite and the finite, between what is visible and what is hidden. Reflections on the night sky. Olbers' paradox reminds us that even the most ordinary experiences, like gazing at the night sky, can reveal profound truths about the universe. It challenges us to think deeply about the nature of light, time, and space, and appreciate the mysteries that make the cosmos extraordinary. As we continue to explore the paradoxes of existence, let us carry with us the lessons of Olbers' paradox. That the universe is as much about what we cannot see as what we can, and that every question we ask brings us closer to understanding the infinite beauty of the cosmos. Zeno's paradoxes, the illusion of motion. Imagine for a moment standing at the start of a path that stretches out endlessly before you. You take a step forward and then another, halving the distance between yourself and your destination each time. But with every step, the remaining distance seems to divide infinitely smaller, each step taking you closer, but never quite allowing you to reach the end. This is the heart of Zeno's dichotomy paradox, one of the most famous riddles of the ancient world. First proposed by Zeno of Elea, a Greek philosopher living in the 5th century BCE, this paradox challenges our understanding of motion and infinity. It asks us to consider a simple question: how can anything ever move if space can be divided infinitely? The dichotomy paradox. Infinite steps, finite journey. At first glance, the dichotomy paradox seems absurd. After all, we move every day. We walk, run, drive, and travel vast distances without considering motion mechanics. But Zeno's thought experiment forces us to pause and consider the nature of movement itself. If every journey can be divided into infinite smaller steps, how can we ever complete the journey? To break it down. 1. To reach a destination, you must first cover half the distance. 2. Then you must cover half of the remaining distance. 3. This process repeats infinitely with each step halving the remaining distance. Logically, no matter how many steps you take, you will always have some distance left to travel. In essence, the journey is composed of infinite steps, and if it takes any time to complete each step, it should take an endless amount of time. And yet we know we can reach our destination in the real world. How do we reconcile this apparent contradiction? Modern mathematics offers a solution through the concept of convergence. The infinite series of steps, 1/2, 1/4, 1/8, and so on, adds to a finite sum. This is because, in the case of the dichotomy paradox, the sum of all the steps converges to the total distance of the journey. But while mathematics resolves the paradox on a practical level, the philosophical implications linger. Zeno's dichotomy paradox invites us to question the nature of infinity and our perception of time and space. Is motion truly continuous? Or is it an illusion created by how our minds process the world? The arrow paradox, motion frozen in time. Another of Zeno's paradoxes, the arrow paradox, deepens the motion mystery. This paradox asks us to consider an arrow in flight. At any given moment, the arrow occupies a specific position in space. In that instant, the arrow is not moving. It is stationary, existing only in that single, frozen moment. If every moment is like this, a series of still frames, how can the arrow ever be said to move? The arrow paradox challenges the very nature of time. Is time a continuous flow, or is it composed of discrete moments, like frames in a film? If the latter is true, then motion might be an illusion, a product of how we perceive the passage of time. Modern physics offers insights into this paradox. In quantum mechanics, time is often treated as a continuous variable. Still, some theories suggest that at the minor scales, on the order of the Planck time, roughly 10 to the power of 43 seconds, time may be discrete. If true, this would mean that the universe operates in tiny, indivisible units of time, much like the frames of a movie reel. But even with these scientific explanations, the arrow paradox leaves us with profound questions. What is time? Is it an objective feature of the universe or a construct of human consciousness? And if motion is an illusion, what does that say about the reality we experience daily? The Achilles and the tortoise, the race that cannot be won. Perhaps the most famous of Zeno's paradoxes is the tale of Achilles and the tortoise. In this scenario, the great warrior Achilles races a tortoise who has been given a head start. Logic suggests that Achilles, being much faster, will quickly overtake the tortoise. But Zeno argues otherwise. To catch the tortoise, Achilles must first reach the point where the tortoise began. By the time he does, the tortoise has moved slightly farther ahead. Achilles then closes that gap, but by the time he reaches the tortoise's new position, the tortoise has moved again. This process repeats infinitely, with Achilles continually closing the gap, but never entirely overtaking the tortoise. Mathematically, this paradox is resolved in the same way as the dichotomy paradox. Achilles' infinite sequence of steps converges to a finite distance, allowing him to overtake the tortoise in a finite amount of time. But the paradox is not just about mathematics. It forces us to consider the nature of infinity and the limitations of our intuition. The concepts of limits and convergence, developed by mathematicians like Isaac Newton and Gottfried Wilhelm Leibniz, were partly inspired by the challenges posed by Zeno's riddles. The philosophical implications of Zeno's paradoxes. Zeno's paradoxes are more than intellectual exercises. They are profound explorations of the nature of reality. They challenge us to question our assumptions about time, space, and motion, and reveal the gaps in our understanding. Are motion and change fundamental aspects of the universe, or are they illusions created by how we perceive the world? Is infinity a genuine, tangible concept? Or is it simply a tool we use to describe the indescribable? These questions remind us that the universe is far more complex and mysterious than it appears. Even the most ordinary experiences, walking, running, or watching an arrow fly, can reveal profound truths about the nature of existence. As we continue on this journey through life-changing paradoxes, let us carry with us Zeno's lessons. Let us embrace the mysteries of motion and infinity, not as problems to be solved, but as invitations to think more deeply about the world and our place within it. The ship of Theseus. What defines identity? Imagine a ship that has sailed the oceans for decades, enduring storms and sunlight, always returning safely to the harbor. Over the years, the ship's wooden planks begin to rot and decay, so they are replaced one by one. First, a single plank is removed and replaced with new timber, then another and another, until every single piece of the ship has been replaced. The question then arises, is it still the same ship? This is the ship of Theseus paradox, a thought experiment that has puzzled philosophers for centuries. First introduced in ancient Greece, it explores the nature of identity and change and what it means for something to remain itself over time. The core question: identity through change. At its heart, the ship of Theseus paradox asks, what defines an object's identity? Is it the physical components that make it up, or is it something more abstract, its history, purpose, or continuity over time? The physical perspective: if identity is tied to physical components, then the ship of Theseus is no longer the same once all its planks have been replaced. After all, not a single piece of the original material remains. But what if the discarded planks are gathered and reassembled into a new ship? Would this reconstructed ship now be the real ship of Theseus? If so, which ship is the authentic one? The one with the same structure, or the one with the original materials, the abstract perspective? Alternatively, if identity is tied to something more abstract, its purpose, name, or history, then the ship of Theseus remains the same, regardless of the replacement of its parts. This perspective suggests that identity is not about physical continuity, but about a sense of connection and recognition. This duality creates a profound tension. Is identity a fixed property, or is it fluid, evolving as the object changes? Extending the paradox, the human connection. The ship of Theseus is more than a question about wooden planks and sailing vessels. It is a metaphor for identity in all its forms, including human identity. The body as a ship. Consider your own body. Over time, nearly every cell in your body is replaced. The skin you had as a child is not the same one you have now. Even the atoms that make up your bones and organs are constantly being renewed. Yet, despite these changes, you still consider yourself the same person. What is it then that defines you? Is it your physical body, your memories, or something else entirely? The mind as a continuum. Our thoughts, beliefs, and experiences evolve. The person you were 10 years ago likely held different opinions, dreams, and fears than you are today. Does this mean you are no longer the same you? Or does continuity of memory and self-perception create a sense of identity that transcends physical and mental changes? Cultural identity? The paradox also extends to communities and cultures. Traditions evolve, languages change, and societies grow, yet they retain a sense of continuity. What defines a culture's identity over time? Is it the preservation of its core values, or its ability to adapt and transform? Modern interpretations and scientific perspectives. The ship of Theseus paradox has found relevance in modern science and technology, raising profound questions about biology, consciousness, and artificial intelligence. In biology, the human body constantly regenerates, yet we perceive ourselves as continuous beings. How do biological systems maintain a sense of identity through change? Consider the process of organ transplantation. If someone receives a donor organ, are they still entirely themselves? What about genetic editing, where DNA itself is altered? In artificial intelligence, imagine a robot that is continuously upgraded with new components. Over time, none of its original parts remain. Is it still the same robot? If we upload a human consciousness into a machine, does the digital copy retain the person's identity, or is it something entirely new? In physics, on a quantum level, particles that make up are constantly in flux, existing in states of probability rather than fixed positions. This raises questions about whether physical objects have a fixed identity or whether identity is an emergent property of larger systems. A paradox for the ages. The ship of Theseus paradox doesn't just challenge our understanding of objects, it challenges our understanding of ourselves. It asks us to consider what it means to be the same over time despite the inevitable changes that come with existence. Philosophical implications. Is identity an illusion, a convenient way to make sense of the ever-changing world? Or is there something more profound, unchanging, that defines who we are and what we hold dear? Embracing change, the paradox reminds us that change is a fundamental part of life. Just as the ship evolves, so do we. Our experiences, relationships, and challenges shape us, adding new layers to our identity while preserving the essence of who we are. Instead of fearing change, the ship of Theseus encourages us to embrace it, to see it not as a loss, but as a transformation. Reflection. Who are we? The ship of Theseus paradox teaches us that identity is not a simple concept. It is fluid, layered, and deeply intertwined with change. Whether we're talking about a ship, a person, or a society, the paradox invites us to reflect on what truly defines us. Are we the sum of our parts, or something more significant? Are we fixed entities, or are we constantly evolving with every moment? These questions have no easy answers, but that is the beauty of the paradox. It reminds us that life, like the ship, is a journey of renewal, growth, and discovery. The grandfather paradox. Can you change the past? Time travel has fascinated humanity for centuries, inspiring countless stories, theories, and debates. It allows us to imagine a world where we can undo our mistakes, relive cherished moments, or glimpse the future. But what happens if we go back in time and change something that directly impacts our existence? What if you could travel back and stop your own grandfather from meeting your grandmother? Would you still exist to make that journey? This is the essence of the grandfather paradox, one of the most famous and perplexing paradoxes in the study of time travel. It explores the contradictions that arise when the past can be altered, challenging our understanding of causality, free will, and the nature of time. The Paradox Explained, a journey into contradiction. At its core, the grandfather paradox is a thought experiment. It asks us to consider what would happen if someone were to travel back in time and prevent their grandfather from having children. By doing so, the time traveler would erase their existence, because without their grandfather, their parent would not exist, and therefore, neither would they. But here's the catch. If the time traveler never existed, how could they have traveled back in time to interfere with their grandfather's life in the first place? This creates a logical loop, a contradiction that seems impossible to resolve. The paradox raises profound questions about the nature of causality, the relationship between cause and effect. In our everyday lives, causality seems straightforward. An event in the past influences events in the future. However, time travel introduces the possibility of causality flowing backward, where an event in the future influences the past. This reversal disrupts the linear chain of events, creating a logical conflict that defies our understanding of reality. Multiple perspectives on the grandfather paradox. Over the years, scientists and philosophers have proposed various ways to resolve the grandfather paradox. Each perspective offers a unique way of thinking about time, causality, and the universe. The self-consistency principle, this principle, proposed by physicist Igor Novikov, suggests that any action taken by a time traveler in the past must be consistent with the timeline they came from. In other words, it would be impossible for the time traveler to prevent their grandfather from meeting their grandmother, because that action would create a contradiction. Instead, the timeline would self-correct, ensuring that the time traveler's past actions align with the events. For example, the time traveler might accidentally ensure that their grandparents meet rather than prevent it. Parallel universes and branching timelines. Another popular interpretation involves the idea of parallel universes. When time travelers change the past, they create a new, branching timeline that diverges from their original reality. In this scenario, the time traveler would not erase their existence, but instead create an alternate version of history. Their original timeline remains intact, while the altered timeline develops independently. Did you know this concept is a cornerstone of many science fiction stories, including popular franchises like Back to the Future and Avengers Endgame? Causal loops. Some interpretations suggest that the grandfather paradox might not be a paradox but a causal loop. In this view, the time traveler's actions in the past are already part of history, meaning they have always happened. For example, if the time traveler tries to prevent their grandparents from meeting, their actions might inadvertently bring them together, completing the loop. This idea challenges the notion of free will, suggesting that events are predetermined and unchangeable. Scientific insights, time travel, and relativity. While the grandfather paradox remains a thought experiment, it is rooted in actual scientific theories about time and space. For instance, Einstein's theory of general relativity suggests that time and space are interconnected, forming a four-dimensional fabric called space-time. Massive objects like stars and black holes warp this fabric, creating the effects we perceive as gravity. Relativity also allows for time dilation, where time moves more slowly in stronger gravitational fields, or for objects traveling at speeds close to the speed of light. This has been experimentally confirmed. For example, astronauts on the International Space Station experience time slightly more slowly than people on Earth. But what about traveling back in time? Some solutions to Einstein's equation suggest that closed time-like curves, CTCs, could exist, allowing for paths through space-time that loop back on themselves. These curves could theoretically enable time travel, but their existence remains speculative, and they raise significant questions about causality and the grandfather paradox. Philosophical implications of the paradox. The grandfather paradox is not just a puzzle about time travel. It is a window into some of the most profound questions about existence and free will. Causality and determinism. The paradox challenges our understanding of cause and effect. If the past can be changed, does that mean the future is not predetermined? Or are all events, past and future, fixed in a way we cannot fully comprehend? Free will versus fate. If the timeline self-corrects to prevent contradictions, does that mean we have no free will? Are our actions predestined, part of a cosmic script that cannot be altered? The nature of time. The paradox forces us to reconsider what time is. Is it a linear progression, a series of moments flowing from past to future? Or is it a more complex structure with loops, branches, and possibilities we have yet to understand? Reflections on time and paradox. The grandfather paradox teaches us that time is not as simple as it seems. It reveals the fragility of causality, the complexity of free will, and the possibility that the universe is far stranger than we can imagine. While we may never fully resolve the paradox, its beauty lies in the questions it raises. It reminds us that the universe is not a puzzle to be solved, but a mystery to be explored. Conclusion. Embracing the mysteries of existence. As our journey through these paradoxes and mysteries ends, we are left with more questions than answers. Each paradox, from the nature of time and identity to the infinite complexities of space and reality, invites us to confront the limits of human understanding. And yet, within these limits lies the heart of what makes existence so profoundly fascinating. The universe is a puzzle, vast, intricate, and deeply interconnected. It offers us glimpses of truth, yet conceals its full story behind layers of mystery. In our exploration, we have encountered questions that challenge our assumptions and expand our imagination. What defines reality, and can it be trusted as more than a construct of our perceptions? Is the cosmos truly infinite, or does it hold an unseen boundary that eludes detection? Can something arise from nothing, or is every beginning tied to an untraceable origin? And ultimately, what does it mean to be human in a universe so vast and unknowable? The beauty of questions without answers. Questions that defy resolution are unique in beauty. These mysteries remind us that certainty is not the ultimate goal of inquiry. Curiosity is. They show us that asking, exploring, and imagining drives humanity forward. Consider the paradoxes we've examined. The Fermi paradox challenges us to search for others in the cosmic expanse, reminding us of our solitude and potential to connect. The twin paradox and Bootstrap paradox reveal the fluidity of time, causality, and existence, inviting us to rethink how we define the past, present, and future. The simulation hypothesis pushes us to question whether reality is a tangible truth or an elaborate illusion, daring us to explore the boundaries of perception. The ship of Theseus shows us that identity is not a static concept but a dynamic process, a story constantly rewritten by change. Each paradox challenges our logic, but opens the door to more profound reflection on the universe and our place in it. A universe that inspires wonder. For all its mysteries, the universe is not a puzzle to be solved, but a source of endless wonder. Its paradoxes and contradictions are not obstacles to understanding, but invitations to think beyond the boundaries of what we know. The power of imagination. Every question we ask opens a new realm of possibilities. Imagination, allosaur, imagination, vision, multi-imaginate, plore time limits, and consider infinity's profound implications. The fragility of certainty. The mysteries we've encountered remind us that certainty is fleeting. As our understanding grows, so does our realization of how much we still have to learn. Our connection to the cosmos, pondering these paradoxes, deepens our connection to the universe. Whether observing the stars or contemplating the nature of reality, we participate in a shared human journey to understand existence, carrying the mysteries forward. The mysteries of existence are not burdens to bear, but gifts to carry. They remind us that the journey of discovery is as infinite as the universe itself. With every paradox, every question, and every step forward, we move closer to understanding not just the cosmos, but ourselves. As we conclude, let us take a moment to reflect on the vastness of existence and the humility it inspires. The universe, in all its complexity, challenges us to embrace curiosity, to marvel at the unknown, and to find meaning in the act of exploration. The cosmos calls to us, not with answers, but with questions. And in those questions, we find the essence of what it means to be human. Let us continue to wonder. Let us continue to ask.